So I believe we are live now. Welcome to the ViodiTV real-time conversation for 12/20/20. And we're very fortunate to have with us on our right, I guess depending on which view you're looking at, but we've got PowerRox and Brian Zahnstecher of PowerRox. He will be talking to us about 5G energy gap. And Marty Snyder is coming to us from Iowa, CICUSA, and I think some other announcements today. He builds the wireless network, not all of it, of course, but I think 30,000 cells or something like that so far. He's built it all around the country and I think other places as well. So we'll be talking about 5G, talking power and where the gaps are, and introducing some new terms. So with that, why don't we start off? As you can see here, we've got a little image here of kind of the various wireless towers that we've seen in the world. From the traditional tall towers that are macro sites to the newer towers that you're seeing on light poles with various form factors that blend in pretty well. And all those are going to require power. And before we get to your kind of power budget, Brian, why don't you kind of give us in your words what 5G is, and then Marty, I'll ask you the same question.
All right, fair enough. And I just want to say thank you very much, Ken, to you and Viodi for inviting me to do this, which is really exciting, and really looking forward to this discussion. Am I coming through all right?
Yeah,
okay.
You look great.
Yeah, I can hear you. Okay, I'm muting myself when we're not talking.
Fair enough. Yeah, so to me, 5G is really a marketing term. It's actually practically something that means nothing. I mean, the real and it's more of what I refer to as the promise of 5G, right? The high level specs, the gigabit bandwidth, the millisecond latency, and all the other cool stuff. That's the promise of 5G, the marketing term, because literally, to me, 5G really is the standard is the 3GPP latest revision standard, which is where some previous generations are driven from too. And so, 5G itself, like I said, it's a marketing term, which is why you hear about, especially major operators and things, they'll say they have 5G plus, and someone else has 4.9, and like I said, I'll give you an exclusive here and tell you I'll just announce 27G right now and leapfrog everyone else, because it's a meaningless term that's purely marketing. No one owns it. There's no such thing technically as like the 5G standard. And so to me, the promise of 5G is really those things, that the enhancements that are coming to the network, those specs and all the bells and whistles and all the cool stuff we're supposed to do, to me translate to the lens of energy efficiency. And there's the potential for great, tremendous growth and need in the energy footprint, but at the same time, there's also tremendous opportunity for energy savings. And as we continue on the discussion today, hopefully we'll make the point too that perhaps the fate of one is actually very closely and inexorably tied to the other.
Oh, you're muted.
I mentioned that we are getting a little bit of noise in the background, although it's just cleared up for whatever reason. So that's good. That's a very crisp definition. And I am pleased that we got the exclusive that 27G is the next generation. And you must be thrilled with that, Marty.
Yeah, you got the scoop.
Yeah, because that means a lot of work for you. But, you're out in the field. Your folks are out in the field. What does it mean to you?
Well, 5G is a marketing term. Brian's absolutely right. We've seen, although it wasn't touted, 1G, but there's been 1G, 2, 3, 4, and now 5G. That to us, it just represents the next generation in technology. And these systems are incredibly expensive to install. It's infrastructure throughout the world. We have 350,000 cell sites or more in the United States. So I I look at every generation of equipment that an operator constructs and builds to offer wireless services as a distinct, change, and they don't want to do that very often. It's pretty expensive. So 5G to us just means the next generation in advancements in technology, and with every advancement since 1G, we're getting more throughput, faster bit rate, stuff like that. So I see 5G as the next generation in technology.
So, Brian, we first met about 5 or 6 months ago, I guess. And one of the things, you had just written an article on the 5G power gap, and that led to you being, I guess, co-chair of a working group within the IEEE. And you guys have just published, I think, a 30-plus page white paper on this topic. Perhaps you can kind of give us an overview of, your initial concerns that led to that article and kind of where the working group is going.
Yeah, absolutely. And thanks for bringing that up, Ken. And certainly, afterwards, we're happy to share the, any whatever links or references we need for the audience to enable them. But so within IEEE, they have a future directions group. And so they tend to create these initiatives, which can be multi-year initiatives, especially for emerging things and kind of hot areas of technology. So, for instance, there was something for IoT, there's something in blockchain, big data, green ICT, all kinds of things. And one of those was originally called the 5G Initiative, which they rebranded to now call the Future Networks Initiative. So it's 5G and beyond. And there's a bunch of stuff within that, but one of them is a roadmap effort. And that's been going on for a couple of years now. And the first generation of that was released at the end of last year, which I believe you're referring to. And again, that's freely available online. We can share that information with your audience. And I was part of that. There was a working group called Apps and Services. It was kind of a miscellaneous catch-all because for this, power and energy efficiency stuff. I'd had some recognition and involvement in the kind of 5G networking world as I came before that from the data center and then ultra low power worlds, but involved in another kind of community around that focuses a lot in the telco ICT area, where I observed some very strange things or very potentially troubling things from an energy perspective. That again is kind of implied by the promise of 5G, and so that's what I initially called the 5G energy gap, which was that first short article, kind of a short op-ed you referred to that came out at the end of last year. And then within this working group, I started to realize I thought the value of that message and folding it into what is essentially this 5G roadmap. Which they've rebranded, so that's now referred to the International Network Generations Roadmap, the INGR. And essentially, from that little content I had in the beginning, it seemed to make sense that there's enough of a story to tell around energy efficiency that we said, well, maybe we should break out an entire dedicated working group. So as usual, especially in any volunteer type of thing, as everyone knows, if you mention it or suggest it, that suddenly means you own it. And so that's how I became the founding co-chair of the Energy Efficiency Working Group, when that along with my colleague Francesco Carabolante of IoTissimo. And now with that, we said, okay, what they were doing is, like I said, that first edition was released, and so the second edition, there were some new working groups added, and that's where the Energy Efficiency Working Group was one of them. So what we did is, since we weren't part of the first edition, and the second edition will not be shipping till essentially early 21 to the public, we created a white paper as kind of an interim thing to frame up our value position, what we're about, and especially to identify some concepts and hopefully start educating the industry on this stuff. So that's what exists now. That got put out a couple months ago, and that's the 20-something, 30-page document you're referring to, and that is also the best resource I would refer people right now if they really want to get the full story. But a preview of that story is we take this concept of the 5G energy gap, which is basically a concern that says once you look at the entire power value chain, as referred to, and I think you were flashing up an image there.
Yeah, unfortunately, I lost it. I'll get it back up here.
Yeah, no worries. Is that there's a concern that because of the very large multiplier of energy demand when you go across the whole network end to end, essentially even really tiny devices. As a matter of fact, the further to the edge you get, the further from the power plant where the watts are originally generated, kind of the higher price you pay in a metric we're calling power cost factor. So it's basically a higher multiplier, right? Where that can be on upwards of 5 or 6 orders of magnitude. It's actually quite shocking. So all those microwatt devices and all IoT doohickeys we talk about could actually require 5 to 6 orders of magnitude per device from the source. So what it says, when you aggregate all this, we talk about scaling all these billions or even trillions of tiny power devices out there. There's a concern that it has a very disproportionate impact on the grid, and is there actually a risk to the grid itself? Due to this massive deployments and of IoT things and wireless sensor networks and whatnot. So that's the 5G energy gap, and then we expanded in that to other concepts that kind of try and break out more and separate both the technical side of the analysis and the economic side, since economic payback period is the huge $64,000 question in just about any conversation around 5G. And so we also have something called the 5G economic gap. And then we realized, that it directly ties to socioeconomic factors too. So kind of have a hybrid of those two concepts, so people can assess things from kind of a purely technical perspective, an economic perspective, and to merge those and to harmonize those into even realizing a socioeconomic one. And we propose some other metrics, like something we call a 5G Derate Factor, so that we're hoping that we want to create all bunch of model analysis terminology around what we hope to be the future common currency, the only common one we know of across every stakeholder and block in the network, which is energy, right? So the currency of energy is what we want to normalize everything around, and that's kind of what the high level premise of that roadmap effort, the white paper, and the 5G energy gap and all those things are about.
Yeah, and I apologize for taking so long to get this up here, but it's amazing the ecosystem when you put it up like this, just the spider web of relationships.
Yeah, actually, the whole point of that is if it looks like a total mess, that was very intentional. The whole point is to say this is kind of the reality of how things are today. And that's part of what we're trying to address. We're trying to take something that looks like the Wild West, where a bunch of stakeholders who are focused in parts of the network or parts of the black boxes in that whole chain. And we want to give them a language to speak with each other, to work with each other, to be able to perform assessments end to end from anywhere in the network and at the high level. So it really impacts every stakeholder, whether you're deploying a device, whether you're a network operator, a data center operator, anything to do with telecommunications, or even on the utility or grid side, if you're not on the hardware or software enablement side.
And it's you kind of bring a unique perspective to this, because it shows right in top of your head there. You've got a resistor, it looks like, and some other things in your logos, I think a capacitor and inductor and so forth. But you look at things from at the very component level all the way through the system. And this, when you talk about IoT things, you're talking about individual small components versus a system, right, for the entire 5G.
Yeah. That's correct. Absolutely. We look at it, like I said, the common thread, the one lens we look at everything through is through energy efficiency, right? The architecture, distribution and utilization of energy at every point in the network. And like you said, we look at that from all the way from the component right? And kind of semiconductor level, subcomponent level, to, you know, system level and equipment level, to, you know, base station, and then network, data center, to global utility levels, and how they all interrelate and everything. And so within our working group, we also have stakeholders that represent all of that. So, you know, we have several folks from, you know, the uppers you might expect from, you know, places like Ericsson, Huawei, Nokia's, those types of folks. Some folks who build, also doing some unique stuff in the radio space. Folks like Derate Communications or New Edges, as well as folks that represent, you know, stuff in the semiconductor space like Global Foundries, and major players in even the data center, people who relate to that. So like HPE is very involved in this effort. And there's a handful of other, you know, folks from, whether they're from power electronics or other key stakeholders, like even a little bit from academia. Linköping University in Sweden is very well known in this space, and even Lawrence Berkeley Labs here locally. So we have some kind of you know, government lab representation too. So we really try and make sure we cover that very wide disbursement of stakeholders, because anything in the world of electronics needs power and needs energy to run and needs to be optimized. And so, yeah, we touch everything.
Well, and this is going to get into a little bit more of the conversation that, you know, shows here energy generation and energy sources. And Marty, that's kind of how we met, because I was doing some research on a video that I'd done a couple of years before. And one of the challenges I think you faced is sometimes having enough power. And why don't we kind of talk to, you know, first I gave a very high overview of what you do, but why don't you give us a little bit more background of CICUSA and some of the installations you do, whether they're primarily urban, rural, and while you're doing that, I'll pull up a couple of images from your website.
Sure. So CIC is a builder of infrastructure. So we've been involved in the development of the cellular networks since the 90s, since the mid 90s. And so our role is to make the wireless communications work. And we have built everything from 1G. We've been around for a while, and from 1G to 5G. So we're now going through the networks, the same towers that maybe we constructed, you know, decades ago. We're back on them and upgrading the equipment at those sites. And we don't just do it for the wireless operators. We also do it for public safety networks. And actually, utilities are a big user of wireless networks for, you know, their internal transmission and control. So what I think part of why you brought me in on the conversation with Brian is Brian's identified that energy is going to become maybe something that's very, very serious and questionable. You know, that now with 5G and with the just a growing dependence of our culture and society on wireless networks and becoming virtual is going to increase the number of devices by magnitudes. You know, it used to be the phone company, you know, had a telephone in every home. When I started building cellular infrastructure, less than 10% of the population had a cell phone. And I watched the, you know, the what we call the cellular penetration rate climb from, you know, under 10%. I'll remember when it hit 50, and then I remember when we exceeded 100, meaning now every human being, there's a cellular type device for, there's more devices than there are people in the United States. And that's because, and now our culture and society is completely becoming dependent on wireless communications for lots of things, and people are coming up with new ideas. And so the idea of an autonomous vehicle, the idea of our refrigerator, giving us a call and telling us to get some milk on the way home from work. All these ideas that people are using to promote wireless and to promote new products and advantages and, growth and in industry and culture in general require more devices. And Brian's identified that all these devices have a power footprint. And we can't just blithely ignore what that means, and hence the working group that Brian's created. So our latest work has been in power upgrades. We do solar work, but we're also getting involved in a new form of energy storage, which is green and clean. It's not chemical based, and it's more efficient. And that's the use of capacitors now for energy storage. And those are starting to be used in cell site because they actually store energy more efficiently, capture it more efficiently from solar, makes renewable energy more useful. And so with this growing demand of energy, the operators, the wireless carriers are now thinking about what does power mean to us and how do we protect, future-proof ourselves against this growing demand for energy. So that's it.
That's super. And actually, I'm showing the supercapacitor on there, and we can talk to that in a moment. But first, before we go too far, a question was asked from on the YouTube chat. We have a student working on the very topic of energy efficiency and 5G. So yeah, this person has many questions and would like to get in touch with via email if possible. Is it okay if I put your emails on the public chat, or should I have that?
Absolutely,
Yeah,
it's
sure.
fine for me. Busy at
Okay.
PowerRox.com.
Okay.
Yeah, and Brian's the guy for energy efficiency and devices.
Yeah. So
And especially if you think that I'm totally full of it and all this stuff, and I'm a naysayer just to freak people out, then by all means, let me know. Good, bad, and different. These are discussions we have to have. That's really the point of all this.
Well, and one of the things I want to go back to a conversation we had yesterday. One of the neat things is that Marty brings some, some actual measurements from the field as far as what he's seen with the upgrades he's done to 5G. And I don't know if you want to talk to that for a moment, Marty.
Yeah, I will. So as we've gone from 2G to 3 and then 3 to 4, they're adding equipment, and then also the purely just from the cellular growth, the number of devices, the fact that you can now stream live video on your wireless phone, listen to music. You got Spotify and the different services where people are streaming data at really large rates. That requires more bandwidth, and more bandwidth means more equipment, more radios, more channels. The FCC has been releasing more spectrum, for wireless operators to use. And with and you can see from the auctions that they've had, the original cellular networks were given away, basically in a lottery in 1984. And then in 1995 was the first major auction of additional, cellular wireless spectrum, the PCS auctions. And then since that time, there's been over a dozen different auctions or a dozen different bands of additional frequency being released. So all this requires more equipment at a cell site. Where that affects a wireless operator is now his power demand at a site is climbing. And that particularly affects off-grid sites where they need solar or just a generator, whatever they're using to supply the power. It requires upgrades. We're doing those upgrades. And what we realized is no one really, we were doing this for, household name operators. And they were just, kind of going through building a network. And no one was really paying attention to this increasing energy footprint. And so it took us doing an upgrade for a wireless site for one of the major operators that was off grid, and we had to bring the energy in for it. And we needed to know what's the demand, like what is the energy footprint. If you talk to a seasoned solar installer, that's the first question he asks. What's your energy requirement? You know, what's your footprint? And so we started testing sites and collecting that data in a high level of granularity so that we could understand what radios were requiring how much energy and at what times of the day. And that was necessary to design solar off-grid sites, but it also gave us a vision or a picture of what the real energy requirements are for these wireless, sites, I guess.
It sounded like it was a significant increase, right?
Yeah. Oh, yeah. Well, I think so. We had sites that were operating on probably less than a kilowatt hour of energy, so less than 1,000 watts per hour. And we have sites now that are using as much as 7.8 kilowatts or 7,800 watts per hour.
It's amazing, and that kind of touches upon the concept that you brought up, Brian. And by the way, I think you have someone who's highly eager to join your team on the energy efficient working group. By the way, looking at the chat, but this whole concept of a watt in gives you milliwatts on the other end, right? I mean, you're talking orders and orders of magnitude, right?
Yeah, very much so. And I think people. Marty was really kind of starting to paint the picture, and I think people really got to get the big picture, right? Like he made the point that said, when you're talking about a cell site or putting a new deployment on, and I'm sure it's the same, greenfield, brownfield, whatever, whether it's new or an upgrade, power is the first question they're going to ask about, right? And there's a good reason for that. It's not just to say, do we have enough, and we'll, tie into economics, but see, people got to realize in the global ICT network, the power footprint, the power pie of everything globally, which includes, not just the cell sites, the base stations, the data centers, the UEs, the user equipment, the phones themselves, and everything in between. That if you looked at that whole power pie, 60 to 80% of that is base station power alone. And that's stark when you look at that of the entire thing. People think it's these mega data centers and all that. No, actually, they're relatively a drop in the bucket to the overall ICT network consumption. And so that also means that they're, and by the way, the reason for that is mostly attributed to the awful efficiency of the power amplifier that's used, typically a linear power amplifier, and then the LPA, which have efficiencies in the, you're lucky if you even get the double digits. So what that means is, for every watt going into that power amplifier, you get maybe 8 to 10% of that kind of in your usable power for your radio, your RF power, and the rest of it is just dissipated as heat. So when and that's why we talk about the power value chain in terms of those blocks. So if you looked at that base station as a black box from input to output, where the input's, it's hooked up to the grid, getting its power, and on the output, like you said, it's transmitting power from its transmitting antenna, right? That end to end, that whole base station is, even best case, on the order of about 6 to 7% efficient. So, that means that's you have to generate almost 20 times the amount of energy from the power plant when you do all the math to what gets to have that 1 watt to transmitted energy. And then that translates to the wireless link is actually where you lose the majority of stuff, where you can lose anywhere from 3 to 6 orders of magnitude. So that, transmitting that watt gets you roughly, on the order of a milliwatt. And again, it could be several orders of magnitude lower than that at your device. And so, and then, you look at stuff kind of upstream, downstream, and all that. So when you look for all the pieces of the network, where are the opportunities? Certainly you look to who's consuming the most power now. Well, it's base stations. And within that, the linear power amplifier, that is a perfect area to focus, because that is also the attributes for the far and away the majority of those losses. So the low-hanging fruit says, hey, if we put our focus and even in making an incremental improvement in, in the power amplifier efficiency, we'd make a significant impact to global energy efficiency. But until we really improve the efficiencies of those, the opposite of that is dissipated power. And that goes to exactly what Marty's point was, and why things have these huge heat sinks on them, why they're warm if you're near them, and we can basically do much better. And I think that also gets to one other very important point that Marty was highlighting, which is energy storage. With the opportunity to really optimize and enhance, base station power, along with all the other parts that we're looking at, from, individual network components to data centers, front haul, back haul, and all that, is our ability to, we want to utilize, be more intelligent with those watts that we get. And, a combination of, renewables and energy storage can absolutely be a major player in that. Actually, in my opinion, even getting outside of the 5G world, you might hear lots of things about energy storage, whether it's for residential use or, what to do if you have solar, all the way up to grid level and grid scale energy storage. And it really is kind of the big, most critical factor, and also the part that's very enabling to many other things. So it's really important to highlight that, as Marty has, and also for people to put more of an attention into thinking about energy storage in perhaps different ways, because all these things tie together. Absolutely.
I want to hold that thought on the storage. Let's go back to it, because I think that's an important thing tying with the grid. There is kind of two questions. One comes from the YouTube chat, and that is the data available, for the energy usage of each radio? And then my question, which I think relates to some extent, does having more small cells help in terms of, that power loss budget? Because now, you're closer to the end device and so forth, versus having the macro cell and, assuming it's fiber fed. Have you guys looked at that difference? Is it significant?
I haven't looked at that. We haven't had the opportunity to collect data on small cells. But if you look at like the wireless operators' plans for deploying small cells, it's not insignificant. Each wireless operator, let's say the big two, I guess it's now the big three, have, each collectively, each probably, I'm guessing, I don't really know, but I'd say 50,000 each macro cell sites. I would imagine that the Sprint T-Mobile merger, they might actually have more than 50,000 combined. But then they have the small cells they're deploying, and their plans to have 1 million, we're talking about 50,000 macro sites compared to maybe 1 million small cell sites. That whatever the energy consumption is, it needs to be thought through and paid attention to. But I don't have data on small cell energy consumption.
What about you, Brian, and your modeling and stuff? It must be a challenge, because you have all these different radio types and so forth.
Yeah, actually, it's one of those things that kind of, like, when you first think about it, it seems like it's not that difficult. It's like, okay, there's only so much power consumed per base station. Seems like a fairly simple arithmetic exercise. But in fact, it's highly, highly convoluted, which actually is kind of the reason which has scared people away from trying to culminate this type of kind of global analysis that we're doing in our working group. And so, like Marty said, there's a major shift. The one thing we know about, no one's arguing about, there's a major shift from a lot of traffic from the macro cell tower model to, the small cells. And by the way, even what you call a cell can vary. right? So, people might have heard of femtocells, or, I've even heard as small as attocells, right? But basically just means
I haven't heard
smaller
that
the
one.
cell, the less area it covers, or the less number of people it serves. And then there's a whole discussion about, which frequencies are served, and the pros and cons of that, which is more than willing to get into at the moment. And there's also offloading, right? Again, of what is a small cell and what is a network. For instance, if there's all this, in the promise of the millimeter wave stuff, and we're talking about, starting to be above 6 gigahertz bands, when they open that up, there's incredible bandwidth opportunities. But in general, the higher you go in frequency, the shorter the range. Basically, the faster the signal dies or attenuates.
Mm-hmm.
So things have to be closer. So we have to get smarter about kind of the local networks, and it depends how densified your environment is. So it's not going to be the same answer for, a building in the middle of downtown Tokyo versus serving a rural town in Topeka, Kansas, right? And so you just make that point, because things like, Wi-Fi, some existing networks that are already there, and other kind of point-to-point mesh type networking things are all going to be required. It's going to be, everyone's going to have to play nice together in the sandbox, and that's where the concept of heterogeneous networks or HETNets come from. You might hear that a lot associated with 5G and the backwards compatibility that has to still exist too through 4G, 3G, and even I think 2G just got turned on in the US. So back to that simple arithmetic exercise, right? Well, if Marty says we're going from roughly 50,000 macro cell towers that are on the order of, kilowatts, right? Maybe in the ones of kilowatts. So now if we transition much of our traffic to, 1 million small cells, how does that play out? Well, on the bright side, right, small cells, as they imply, are smaller, and as you might imagine, have a much smaller power footprint, right? So maybe they're more on the, on the order of 100 or less watts. I mean, I'm generalizing because there's all kinds of flavors here, and ideally, the more in the future we get, the smaller they get, the higher in frequency we go, the smaller their total power output should be, which is a great opportunity to address that, base station 60 to 80% power pie issue, because with the smaller they are, the faster you can turn them off and in real time. So these big macro cell towers, they kind of dial the power up, dial it down according to predictive traffic patterns, where if the power is small enough, we can literally turn them on in milliseconds and adapt to real-time conditions without having to take a guess at it. And that's where there's tremendous power-saving opportunity. But again, how do the numbers flesh out if I'm going from, in this one area, if I was serving it with, 5 of these larger macro cell towers, and I transition that to, 100 or even 1,000 small cells, the jury is really out to say, how much between the power we save at the macro cells to, we may have, the small cells may be lower power, but there's also many more of them. But they're also have much better dynamic control ability and all that. So when you really start to look at it, and then start to look at the network level and all the hooks and all the knobs that are there to turn, I said the jury's out. It's far more convoluted than I think is realized. So the last bit of that, kind of what you're saying is, so what are we doing to address that? And especially in our working group is, identifying kind of the roadmap, right? The 0, 3, 5, 10-year outlook as we predict, and what's needed, even if it's not kind of on the horizon, and what is achievable from, network efficiency, or what it needs to be. And by the way, there are groups who did focus on doing this in the last decade or so. I give a shout out to Green Touch, and as well as the Earth Network Initiative. That's for your our academic friend who's asking a lot of questions. So I'll give a teaser to look into.
Those are referenced in the white paper too, as I recall.
I believe so, yeah. And
Yeah,
if not,
there's
certainly
in the
reach
table.
out to me. That and any one of my million presentations on it, I could certainly give you. But so that's why essentially in that power value chain and all the black boxes in the network that make up a global network, we need to use that common currency of energy as our common language and some common metrics that we can use to characterize all these black boxes, and then therefore get them to, have a normalized a way to connect them all and assess them from a technical, economic, and socioeconomic perspective. And so that's really a main goal, and which includes, being able to develop models that make sense for all those network constituents, and then being able to run simulations that, yield something useful for them, and enable, an engineer who's designing a radio at Ericsson to have this same discussion with, a business person that's doing the payback period analysis at AT&T, and for them to also, do that same analysis, same modeling, and talk that same language with the local utility grid, for instance. And that's really, a core motivation for all of that.
And it looked like you'd probably seen the chat based on your answers there, because one of the questions was, what about, reducing the base station power and so forth? And you kind of addressed that with the idea of turning on and off power. Like you said, the best watt is the one you don't use, or something. I paraphrase what you say. And that was one of the questions. The other one was, how do you have any do any of these two have any operator data, and not just the physical layer, but the upper layers also? And when I'm thinking about the upper layers, one of the things that it just struck me was the interoperability that's going to have to be there as 5G goes to standalone, as it start, because it won't have some of the features in initial, like low latency and network security and slicing. Those are supposed to be developed, and it seems like there's a lot of uncertainty in that area right now. But it seems like it would be important too for this interoperability for power base stations, for things like if you're roaming, that it knows that you're there or not, and that it'll turn down the station appropriately.
Yeah, it's those intelligent hooks that we really want to take advantage of. And again, it's to go through those at all those levels is far more than we have time or probably audience energy for. Pardon the pun. But certainly, you see a lot of those questions, and they're great questions. He's going down the rabbit hole in exactly the right way. But we'll just have to, part of it, we'll have to tell him we'll address more of that offline. But in general, sure, there's data from anecdotal data to even when I talk about the power value chain, it's a basic napkin math thing. There's nothing complicated about it. No complex equations, but I just look at kind of the general efficiencies of each of those black boxes. You add them all up, and that says how much has to be going in to have so much out at the end. But again, like most things, it's not that is certainly an oversimplified view of it. And the people who have the real data, right, like the radio folks and the network operators, and then folks like Marty, as he was alluding to too, a lot of time they like to keep that pretty close to the cuff. And there are, they will publish kind of larger aggregate things. For instance, Ericsson puts out what they call their wireless mobility report every year, which is usually very good, has lots of good stats, ties a lot of these factors together, even including things like carbon footprint and some of those, socioeconomic kind of connecting the unconnected factors. But folks like Marty, I would say, have the best real data, because that's not, even the Nokias and Ericssons and Huawei's of the world, sure, they'll have lots of data. And even if they are willing to share it, it's from their own stuff. And, you got to assume it's probably, has their own bias to it or something, something that makes their equipment look better than the competitors, usual stuff, usual benchmarking stuff. But folks like Marty, the people who really just deploy the stuff and the integrators and have real data of real applications and real towers, I think that is probably the most interesting, kind of most useful knowledge. And then, but of course, just like those other companies like to keep that stuff close, right? Marty's also is working. Those are also his collaborators. So I can defer to him to kind of comment on this. But a lot of time his hands may be tied because they, for the same reason they don't want to share their own data, they also perhaps exhibit some control over what he has, and there's probably some confidentiality factors and other things involved. So yeah, there's lots of there's data, there's piecemeal data out there, but like I said, I identified some of the kind of the challenges of getting it. And actually, one other important point that I was alluding to so much before about the need for commonality in our analyses is that doesn't exist today. So it's totally apples to oranges, right? You'll see tons of data and even through our initiative and through the many 5G tutorials that have been put on around the world for the past several years in the World Forum. Lots of great data and interesting stuff, mostly from especially a lot of academic institutions. A lot of things focus on spectral efficiency, kind of bit per hertz per watt type of thing, and perhaps per joule, depending on how you're looking at it. But they're all in different languages and in different, technical language and different metrics and different models. So it's so apples to oranges. You can't link them all together and say, here's a harmonized model. And so that's part of the normalization that we're trying to, normalize everything to that currency of energy again, to enable more of that. And perhaps that'll also even help folks like Marty, who even if they can't, disclose specific things and all that, they can help with that normalization, and that might give them, kind of an ability to help contribute to the need to collect this data, assess it, do analytics on it, and drive improvement with it, kind of in a feedback loop, in a way that perhaps his hands are tied today. Though I should stop speaking for him. Let's hear it straight from the horse's mouth.
Which is ironic because we have a picture of him riding a horse. So.
Well, you guys asked me the other day. I did get permission to share some of that data, so I'll be happy to send you the CVS files or CSV files, sorry, and you can start coming through it, and we have more coming up. We have plans for a lot more data collection on the books. So I'm excited about that. Actually.
That's great. Yeah, I'm super excited. And honestly, anyone watching this, if you're not excited, but this topic is of interest to you, then you should really look into this and ask yourself, if you're not excited, why? And you're missing something. So you should be excited. Trust me on that one.
Well, speaking of exciting announcements, yesterday, and I still want to get back to the storage and distribution topic, but yesterday, I think it was yesterday, there were some announcements about ORAN and its impact on potential power. And I'm just curious, this is the Open Radio Access Network, I think is the acronym, but the idea of, kind of common radio heads and standardized interfaces that way. Just your thoughts on ORAN as far as implications for power.
Well, I can tell you right now that will have huge implications for power footprint. It will reduce power consumption by magnitudes. What ORAN is, what we're talking about is sharing spectrum, sharing radio equipment, and routing calls. So today every wireless operator in the U.S. has their own infrastructure. They're separate pieces. I like to tell the story about my mentor, my radio frequency mentor. He built my radio mentor built the first, or designed, I should say, the RF plan for the very first cellular network in America.
Wow.
Which, by the way, was in Minneapolis and Chicago in 1984. And from his own mouth, he'd say to me, "Why is everybody building their own network?" He goes, "We should share this." Because he saw there is a redundancy, or there is duplication of effort with each carrier developing their own infrastructure. ORAN is a movement, and it'll take a lot of energy, pardon the pun, but it will take a lot of energy to make a cultural shift to that kind of architecture. But it'll be a shared architecture, and therefore shared energy costs and less energy consumption. Cut it in half. at least. So
that's huge. And Marty, you're okay if I share your email with the?
Sure. Yeah. Yeah.
Okay, it's actually on your website too. That's how I found you. So
they'll find me. Anyone can find me. I'm not hiding anymore.
And Brian, do you have any comments on ORAN or?
Well, I guess it's more kind of the open part in general, because I'm not, the actual radio specifics and from standard to everything else is a bit outside of my wheelhouse. But I see it analogous to, and by the way, I should qualify my statements that I am a hardware guy, right? I'm a hardware engineer through and through. So just be aware of the biases that are built into these statements I'm about to make. But essentially what it reminds me of is what was done in the data center world through the Open Compute project, right? Which is basically, in my, myopic view of it, it's really the idea that everyone, the operators and everyone, like you said, on paper, sharing that overhead and everything makes sense from an energy savings perspective. Anything that saves energy, I'm all for, right? I'm not selling anyone's equipment. But in general, I feel like it's kind of the idea is to basically abstract hardware initially and to commoditize it, and then to commoditize essentially everything to be open everything, because really, the winners of that are the operators, right? Not everyone else in the supply chain. So like, there's a reason that it was, Microsoft and Facebook and, eventually Google and folks like that were very involved in the Open Compute project, because what they said is, let's just commoditize this hardware. And eventually, again, they did to all parts, from the servers to the racks to the power stuff to even, and then even the software stacks, which I'm even more novice and shouldn't be talking about. But the point is what now, was that great for the people building the equipment and all that and all that? No, because it kind of takes something that, like you said, was specialized and owned, and to Marty's mentor's point, from a pragmatic standpoint, why is everyone doing their own? But from a business standpoint of, what's mine is mine, and I can run my margins off of that, is there's certainly business and economical motivation for doing things like that, at least in a, again, shorter, smaller sense. So that's how when I hear things like ORAN, I hear of a desire to standardize stuff basically as much as possible, right? To commoditize it and to essentially abstract it from the economic part of the analysis, so that essentially the real value, the thing you deliver is the service, right? It is, just like we know, today it's not even about hardware. I have to, when I talk to all these software folks and their magic apps and stuff, sometimes I have to remind them, hey, everything actually runs on hardware at the end of the day. And
Right.
And believe it or not, technically there's no such thing as digital, right? Everything's technically analog at the end of the day. But people are so far removed from that, and even, I mean, I say it somewhat facetiously, but it really is. If you talk to younger engineers, it's like they just, you turn stuff on, stuff just works, you access stuff in the cloud, there it is, boom. And I think I see ORAN and the desire to try and, open source, sounds all great, but there's definitely losers in that equation too. Now, one last point about, specifically bringing commonality to the Radiohead. And again, I'm going to tread lightly since I'm mostly speaking out of, complete novice here. Is that, with the many different frequencies we talk about, especially when they start getting way into the upper side of the millimeter wave bands and all that, software defined radio stuff, all that self-optimizing network intelligence that has to occur. And as we talked about, even different flavors of small cells and everything, that will need to occur. It's hard to say, well, if we just pick the one design that works best for all of these, what would it be? And you'd say, well, there's never going to be one. You're always going to be borrowing from Peter to pay Paul, kind of. And so, I think that some normalization makes sense. And even in that OCP community, for instance, they have a telco focus. And for this exact reason, I even said, hey, if we're having ubiquitous small cells, you should consider the 5G small cell as kind of a normal thing in that, in that community, for those reasons of being able to, control things easier and harmonize and, I guess, make standards kind of more, succinct and less nebulous and things like that. But yeah, I don't know, pros and cons to it all, I guess.
Well, actually, we just got a message. Wait, Brian, BZ, I need to charge my phone. Just hold on. I don't know if that's from a friend or something, but it is ironic.
That is a friend of mine, yes, and hopefully he's charging it with energy harvesting. But that's a totally different.
That's a good segue. Energy harvesting. So, that's something that I know is near and dear to your heart, Brian. Maybe we could talk about that, the whole idea of distributed energy charging, harvesting rather, and then storage. And then Marty, we'll go to you, and because you're actually doing this because you have to in some places. So why don't we talk to that for a moment?
Sure. So, in a nutshell, as we talked about, basically that, the further you get to the edge, that you require energy or power at the edge, the higher that power cost factor is you're going to pay for it. So conversely, the more energy you can supplement at the edge, it has a very large multiplier for what can be saved and mitigated from generation. So, for instance, if you actually look at the numbers and even the simple napkin math, it says to have, roughly a milliwatt of received power here at the edge, from best to worst case, from my calculations, you have to generate between about 20 to 60 watts, best to worst case, from the power plant. So again, that's 20 to 60 watts to have a milliwatt of received power here. So that is that we're already talking on about approaching 5 orders of magnitude for that. So, but the flip side of that equation is, for every microwatt or milliwatt that I supplement from something else at the edge, then I will save 20 to 60 watts from needing to be generated. And so that's where, and then there's the scalability is also not, it doesn't all scale linearly either or anything. But so that's where the energy harvesting part ties in, because that's another area that's just been a special focus of mine, because I think it's important for the world. It's a perfect time with this explosion of all these IoT and ultra low power devices and wireless sensor networks. And the idea is to, in the long term, ideally complete mitigation of primary battery cells, or non-rechargeable, basically, disposable hazardous type of things. And use as much secondary or rechargeable energy storage as possible. As Marty will talk to in a minute, at kind of the larger, what I would call the industrial scale, like the energy storage required for a base station or a data center. Which, on a side note, in talking to many telco operators, they'll tell you batteries are the bane of their existence. That for their costs, I mean, aside from, in a cell site, the rental of the real estate is usually the number one cost. But things related to power and energy, and especially batteries, or let's just call it energy storage, and their placement and maintenance are, again, just the bane of their existence. So anything that can make a big dent in that, it will be, hugely beneficial. And so, but a lot of the same concepts apply even at the tiny device level. For energy storage. So what energy harvesting is being able to scavenge ambient energy from the environment around you, right? Not from a directed source. So, a classic thing most people might know is PV, solar, right? But that scales from microwatts to megawatts. Of course, we know of utility scale solar now. Many people in the consumer space even have it on their house. This is my watch. That's a solar panel too. This is perpetually charged. I never have to change a battery. And so, PV can provide, let me say, gigawatts, or it can provide microwatts, and many other forms. You can harvest every type of energy physics affords us, and we don't have time to go through all that. But something that, in the 6-7 years that I've been focusing on and promoting, trying to bring energy harvesting to the mainstream, it's an uphill battle for a lot of reasons we won't go into. But now all of a sudden, if you know what the risk we talk about in the 5G energy gap, now all of a sudden energy harvesting is, I'm not calling it the silver bullet, but it is a very promising, it now has a much greatly enhanced value proposition, because even you can use that to maybe just generate those, a few milliwatts or microwatts or whatever at the edge, and have huge payback. And in the worst and best case scenarios, if what I theorize or what I'm hypothesizing about the 5G energy gap comes to fruition in the worst way, and we start seeing grid disturbances, and kind of like what happened to Germany when they massively deployed PV originally on a grid that wasn't built for it, right? They had rolling blackouts all over the place and everything. Same thing in the energy harvesting world, that if this 5G energy gap risk thing turns out to be true, or we have to derate 5G because of it, then all of a sudden energy harvesting is now a real potential solution, or major contribution to a major solution of it. So that's kind of it at a high level. And it's not just also the supplement, at least as harvesting goes, it's not just the supplement of the the energy budgets of the tiny things. But even like, say, a base station itself, if we wanted to power it renewably, whether it's a PV setup or a wind generator or some combination of others. So at the end of the day, everything is about being smarter with the watts we have, or what I refer to as intelligent power management. Phil.
Well, and that leads to the example of Marty. I mean, why don't you take us through how in some cases you have really no alternative but to generate and store your own energy. And I'll bring up a tab here for you.
Right. Well, thank you. So we've been Brian's been talking very technically about energy and all its nuances and how we can improve and make it efficient. I want to point out, at a philosophical level, this matters to everybody. And Brian said, if you're not excited about it, you should be. But this topic affects the human race. It affects the planet. We have global warming. It's like a real deal. I was born into a world with less than 6 billion people, and I'm going to die in a world with more than 8 billion people. And when you talk to businesses about energy, or about their utility bill, or how many kilowatt hours they need at a site, or a homeowner, the same thing. How many kilowatt hours do you need at your house? And what's your electric bill? It's always typically been a financial discussion. And we as a culture, we as people, tend to look at things in a financial perspective and not think about the bigger perspective. And that is that we have to generate all this electricity. And if we're going to build a 5G network, and if we're going to have, and I think Brian's probably right, billions of devices out there that all require energy, and that milliwatt that requires 20 or 30 watts to meet has to be generated. And that generation in the past and traditionally has created greenhouse gases. And we're burning fuels. It's a wonderful thing that renewable energy is now becoming more economical. That's fantastic. But to make renewable energy useful, we have to be able to store it. And that's why I'm excited, and why you're showing the pictures, and why you invited me here, that we've brought the first non-chemical battery storage device to the United States. We're introducing it. It's new technology, but it's coming and it's happening. And the beauty of the capacitor-based energy storage is that there's no chemicals involved, so it's green. It doesn't wear out. You have a chemical reaction or redox happening inside a battery, which means that eventually a battery wears out because you're changing molecules back and forth across an electrode and an anode, and they get crusty, and so they wear out, and then you got now you have a toxic device that is no good at, Brian made the comment, you talk to an operator, the biggest bane is batteries. They need them, but they hate them. And now, for the first time in history, mankind has created a new device. There's a new technology out there. It's not even really a new technology. It's a new application of a very old technology that we can now use a non-chemical mechanism and store energy electrostatically. And that's what the capacitor modules are doing. We're storing, and we can cycle these in and out 1 million times. A battery, you're limited to 1,500 cycles maybe in a chemical battery, maybe 5,000 with a lithium battery. But nonetheless, after those 5,000 or 1,500 cycles, they're done. They're broken. They're over. They're dead. And here we now have an opportunity to store energy in a green way. It makes the need for generating energy, i.e. dumping carbon into, carbon dioxide into the air, creating these greenhouse gases, it reduces that. And so I'm really excited at a practical level, at a human level, that we actually have a device now that we can say promotes a clean, green planet Earth. And now we need the guys on Brian's team and in the IEEE Working Group he's on to figure out ways to reduce the actual energy demand of devices. We use that. It's another tool in the quiver, if you might say, or another arrow in the quiver. And it allows we need those devices, and we say, hurry up, figure out how to do these different things so it reduces the energy footprint. But we also need more efficient ways to store energy, which we are now into with capacitor-based storage. And together, this is important for everyone, for every human on Earth, because we're taking better care of our Earth. And I just like to look at it in those really simple terms. The capacitor-based energy helps to save the planet.
Well, one of the things that I interviewed the founder of KiloWatt Labs a couple of years ago, and it's taken a while for it to come to the United States. And yours is, when I saw this on your website, that looks like a regular CO, and it looks, oh my gosh, it looks like batteries, but it's not. It's the supercap.
That's a cell site. Yeah, that's a cell site, and that's an old rack that had lead acid batteries in it that we removed, and we
don't have to worry about outgassing or any of that stuff anymore, right? And even an idiot like me could short circuit the thing, right? Flip the cables,
you could short circuit and you'd be okay.
Yeah, which is kind of scary because there's I have images of the Shell Answer man from the 70s and the dummy blowing up from crisscrossing their wires, but that's part of, you've really at these remote sites, a lot of times there is no power. So you have to have, something renewable like a solar, wind, whatever, but then you need the storage and then backup generators. You were explaining how this one remote site, literally the cost of filling up that generator was very costly, almost as costly as the storage.
Well, it was on an annual basis about the cost of the batteries. What we did is that first it's kind of important to understand how that works. There's a mechanical reason why that works. Capacitor-based storage absorbs energy rapidly, i.e. about 10 times the speed of chemical batteries. So by storing the energy faster, we can absorb more of the solar being produced every minute by the sun, instead of like dumping it or it's being wasted or not used. And then two, when we turn on a generator to charge the batteries, which in this case we needed to do, back to the earlier discussion, the cell site was being upgraded to 4 and 5G. The power footprint went way up. The amount of solar available now doesn't meet the need. We got to make up the difference by generating it. If we charge batteries that absorb energy slowly with a generator, we have to run that generator for longer hours. By charging them rapidly, we turn on the generator, we run it for an hour. So on the site that you were showing there, we have now, we've gone from 8 hours of generator runtime a day to 1.27 hours of generator runtime a day. Massive amount of fuel savings.
Yeah.
And now we need to figure out how to just reduce the energy footprint overall from the site.
Which is where Brian comes in.
That's where Brian comes in.
And kind of moving forward here, and I probably should start to wrap it up because it is 2:42, and this might be topic of a further discussion. But what are your kind of takes on moving this into the grid, further into the grid as you get power, these small cells and so forth? The importance of backing those up, the importance of being able to generate electricity locally like that. What are closing thoughts on that?
Brian made a comment about Germany rapidly building solar into a grid that couldn't receive it. That's a real thing. That's real in the United States. It's real anywhere in the world. The grid was designed to function one way. Now we're adding a new element to it. Storage is the solution to that problem. We can absorb that energy being produced by homeowners and by the solar farms, the utility size grade solar farms. Now we store it. We are working together with several large utilities to bring large scale capacitor storage base to the big wind farms, the big solar farms, the renewables, to make them more useful. So that is the way of the future. And operators, anybody with a large base, whether it's all the homeowners in California, whether it's all the cellular operators that put energy storage in their situation, they're helping ease that burden on the grid. It's better for everybody.
Yeah, a couple comments on that. One, actually, I think people don't realize how, even from a energy storage perspective, how many different ways you can really think about and apply it. Like, most of which Marty was just saying. Yeah, of course, like if you have solar, you can store your own energy. But then some people have solar and energy, and they don't care anything about energy storage as long as their whole goal is just to wind back or offset their power bill, right? But then some folks, if you're as solar before it became kind of consumer grade, when it was your only source of energy, may have been something you needed to store so that you could run at night, for instance. And now as we get more intelligent, that there's from both a utilization and an economic perspective, there's different ways to think about it. For instance, you can use energy storage localized for doing something called peak shaving, which says that, most of the time, if you looked at the energy profile, like that data that Marty has of a base station, its kind of average steady state power is pretty low compared to its, the peak that is capable of, that is designed to. High signal to noise ratio, if you will, or peak, high peak to average power, the PAPR, kind of in RF world terms. But the thing is because you actually hit that max or even close to it so infrequently, it's a total waste. If the average is down here and you have to, if on the average the site takes requires roughly 100 watts, and but for peak it's designed for 2 kilowatts, then everything has to be designed to the max, 2 kilowatts. That's in engineering. That's how we're classically trained to think and all that. But today's world is different. And it says that if we could design everything closer to the steady state average and just have something to handle those occasional peaks, there's a huge advantage to that. That's what peak shaving is, and that's another major application of localized energy storage, to say we can now design everything to the much lower average, but we still have the reliability, which is really what counts at the end of the day, especially to these network operators, with localized energy storage to meet those peaks. And this is done. This has been done in the data center for years. We're trying to do it in lots of different areas now, even down to small devices and things like that. So, another way for energy storage, believe it or not, as Marty said, most grids were designed to be unidirectional, and when we put renewable stuff on and feed it back to the grid, we're now forcing it to be bidirectional. So another major function of a lot of having so many of these renewable distributed sites and these micro intelligent inverters that are on them that are directly grid tied, is the grid may actually call on all those things to help in a situation where perhaps if there's a line sag or the frequency is starting to drift. Basically, if the electrical grid is becoming unstable, they actually will call on a lot of those folks to help stabilize the grid. And we don't have time to go into the weeds and how that's done, but I'm just making the point that energy storage, you can look at it from 20 different ways and 20 different applications and 20 different business models. And what they all converge on is Marty's core point is it's absolutely essential and necessary. And that was that. And then, kind of to that idea of peak shaving is also the idea of maybe you even address some of this 5G energy gap and 5G economic gap issue with that. Because kind of like how we supplemented, harvesting for tiny power devices. Well, if you're using, larger industrial energy storage to supplement the base station energy footprint, then that again has a huge impact globally, and you're also supplementing highly inefficient things. So you're killing two birds. Well, you're killing a lot more birds with that one stone. Because like Marty said, today, if you're not storing it, even if you're generating all this great green renewable energy, it could be going to waste if you're not either using it or storing it. So, we talked about how much goes to waste in the base station due to its inefficiencies. So until we really get the efficiency up, at least if we're, wasting some of this more to heat, then let's at least waste heat that we don't have to generate, particularly through non-renewable means, and generating more carbon footprint. Though I did notice, I have to call out Marty, because he seems so big about reducing greenhouse gases. It makes me think he has no respect for trees, because trees need CO2. So, I don't know why you're trying to choke off all the trees, Marty. I like trees
right now.
but whatever, you're entitled to your opinion, sir. No, I say that in jest before I believe in climate change before everyone jumps on me. But anyways, yeah.
Well, I think there's a lot of fodder for future discussion, particularly on this integration of the smart grid, which obviously, to be smart, it needs some kind of telecom network. So if you guys would be interested, maybe in some time in the future, we could have a further discussion in one of these areas of that would be of interest. And,
absolutely, totally game.
And I put the contact on the text message. But again, if you guys want to, on the live chat, if you guys want to say it before we leave, that'd be great.
Awesome. All right. Thank you.
That's CICUSA, right? .com for you.
Yeah. CICUSA.com. Correct.
And then Power.
Yeah, I'm. My email is bz@powerrox.com. My company's PowerRox, so POWERROX, as I've gratuitously and shamelessly put in the background here.
I like it.
So all kinds of things related to energy efficiency and power analysis, from technical to business and otherwise. But thank you very much for having me on this. It's been a great discussion. Clearly, even if it's just that one student, that's where planting these seeds, where we need to cultivate them, because that's also the next generation. So we're increasing our efficiency cost factor for education, and I'm always a big fan of that if it improves global energy efficiency. So thank you very much again.
Well, and this will be posted on ViodiTV with highlights in there. And next week, I'm not certain who's going to be on there. I'm going to be, hopefully Thomas Crowell will be able to join us next week, and we'll be talking intellectual property in this age of video conferencing like this. So that is going to be an upcoming topic, whether it's next week or not, what remains to be seen, but stay tuned on @Viodi. And I'm going to end the stream